Hello, this is Jack Jackson. In this video, we're going to start working on our material coordinating with the third unit, second homework set, continuous probability distributions, and we're going to look at the probability density function, the PDF, and look at more of its properties. So let's review a little bit. In the PDF, the probability density function, probabilities are areas between the PDF graph and the x-axis. The CDF, cumulative density function, the cumulative, left, or less than probabilities are y values, and in general, probabilities are vertical distances on the CDF graph. So for the PDF, probabilities are areas. Keep that in mind. And these are areas between the PDF graph, below it, and then above the x-axis, so between the axis and the PDF graph. And usually there's some, range left and right that you go. So left probability is or sometimes called a left-tailed area. It's the probability to the left of x equals a, and in between the PDF curve and the x-axis. The right probability that x is greater than b, is right-tailed area to the right of x equals b, and again between the PDF curve and the x-axis. And then you have this between kind of probability that a is less than x, which is less than b, is a bounded area between x equals a, x equals b, and between the PDF curve and the x-axis. And the total area under the PDF graph and above the x-axis has to be 1. So the range then is an interval from 0 up to some number. In most cases, it depends on the distribution a little bit, but in most cases that's going to be a fairly small number because the whole area has to be 1. So the whole area can't be very big. The PDF graph may or may not be continuous, one connected piece, but if not, it will only have a limited number of breaks. And so it begins and ends at 0. So on the far right and the far left, it is either on or approaching the x-axis. We could say the same thing this way. The limit as x approaches negative infinity of CDF of x is 0, and the limit as x approaches infinity of CDF of x is 0. Let's look at some pictures. So here are the PDFs of two of the most important continuous distributions. On the left, we see probably the most important distribution in all of statistics and probability, the standard normal PDF, and a sort of a slight variation on that. On the right, a T-PDF. This one has what we call 5 degrees of freedom. And the standard normal has a mean of 0 and a standard deviation of 1. Both of these have a mean of 0. They're kind of bell-shaped curves. Notice that the total area under that curve, in both cases, is 1. And also we see that for that to be 1, there has to be either some end to it on the sides, or in this case it goes on forever, left and right, but it's approaching the x-axis asymptotically in both cases. In this particular case, both of these are continuous functions. They're both symmetric and mounded up about the mean. So the mean, the median, and the mode all equal the same thing. Mean equals median equals mode. And it's 0 in both cases. Here are a couple other examples. These are two important ones we'll be working on later, a chi-square and f. The one on the left is a chi-square, specifically with 10 degrees of freedom. The one on the right is a f distribution. This specific one has degrees of freedom 10 and 20. And if you notice, what happens here is these are 0 to the left of 0. So technically speaking, they go on forever to the left, but that part can be ignored. So this part is just 0 here. So you might as well say it just is defined from 0 to infinity if you want to, because the probability that you get something less than 0 is 0. And then we have a little shape here. Both of these are continuous functions, and they're skewed to the right. They have a horizontal asymptote of y equals 0 on the right, but they actually are y equals 0 on the left. Here are a couple more. This one's called a beta distribution, and it's also 0 from 0 to the left, and it has a distribution like this. This one is actually skewed to the left a little bit. Here's another one, log normal distribution. This one's skewed to the right. This one's called the triangular distribution. Hopefully you can kind of figure out why it might be called that. And it looks something like that. So there are a variety of different shapes you can have, but in every case, this area under this curve, here, 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 that total area has to be 1. And areas under the curve are probabilities. Now, even though the CDFs always have to have actually continuous functions, that is one connected piece, that's not necessarily the case for a PDF. For example, here is what we call a uniform distribution, which is just a horizontal line segment here on the interesting part, and 0 outside of that interval. So in this case, from 4 to 7, the PDF is given by this little horizontal line. Outside of that, that is to the left of 4 or to the right of 7, the probability is 0. So this is in 3 pieces. It's kind of a little step function here. And you have a discontinuity, a break, right here at 4 and 7. You might even call this a rectangular distribution, because the overall shape, if you drew a vertical line up here from 4 and finish this out, you'd have a rectangle of area 1. This is an example of a type of triangular distribution that has a break in it as well. Again, this one also is really the interesting part, is between 4 and 7. To the left of 4, the y values are 0, and to the left of 7, the y values are 0. So the probability is something greater than 7 or less than 4 is 0. And then probabilities that actually happen are stuff between 4 and 7. And this one here, like the distribution on the uniform was a horizontal line, this one is a non-horizontal line segment. So it goes from 4 to 7, and then the y's go from 0 up to some value here. Okay. So that what? So that this total area is 1. So once again, notice that finding probabilities from a PDF curve amounts to computing, or at least maybe approximately computing, an area between the PDF and the x-axis. So what we're going to do in our work a little bit later on as we go through this is, in our next video in fact, is we're going to start working with some distributions that are easy to find areas of. We're going to start working with uniform distributions. So uniform distributions look like this one here. This is the probability between 5 and 6 is this shaded area. It's just a rectangle. So that's pretty easy to find the area of. So we're going to start with things like that. We're also going to do some things like triangular distributions, like this one here, or here, or here. And notice here, it's also fairly easy to do. You know the big triangle is area 1. That's going to allow you to find a formula for that line. And then you know an area of you could find this area here, which is actually a right trapezoid. You can actually find it using a formula for a right trapezoid if you want, but it's probably easier just to think of it as 2 triangles. You have a triangle here that comes with this as the side. The base goes all the way down to 4, and you've got a triangle there, and then subtract off a triangle here. Similarly, you can do this one or this one kind of the same way. So those are called triangular distributions, and we're going to look at those because the areas are can be found from finding areas of triangles. Okay, so in each one of these cases, again, the area shaded is the area between 5 and 6 on the x-axis, and it's under the PDF curve. So in each case, this red shaded area is the probability that x is between 5 and 6. Now, connecting this together with both the PDF and CDF graphs, okay, here's a PDF and CDF graph for the same distribution. Illustrate and estimate x is less than 5 on both graphs. Okay, see if you can go ahead and do this yourself now. Press pause, come back when you're ready. Well, x is less than 5, so let's find 5 on the x-axis. Let's see, look at the scale here. Looks like they're going up by halves, so 5 is right here. And we're talking about to the left of that. So in this case, it's going to be an area to the left of that for the PDF. It's going to be the actual y value here, or that vertical distance on the CDF. So the CDF as we've done before, it's this vertical distance up to, since it's a left, it's from the CDF curve down to the x-axis, that distance, or in other words, this y value that we have across here, which is actually a half, 0.5. If we do this PDF down here, it's this area to the left of this 5, but under the graph. Now, there's nothing under the graph here. By the way, the PDF and CDF are actually on top of each other right here. This is why you don't see any blue out here. It's underneath the red. Okay, now, well, this total area is 1, and I think you can pretty easily see on the graph that you have half of that area. So that's 0.5. You have 50% or half of the total area. So the probability is 0.5. You have a y value here of 0.5. You have a vertical distance here of 0.5. So y values on the CDF are probabilities. That's vertical distances, this green vertical distance on the CDF, but on the PDF, it's an area which we see shaded. Let's try another one. Here is a graph of a CDF and a PDF for the same distribution. This time, illustrate probability of x is less than 3 and approximate it. Press pause. Well, I think you can see here that what we're going to get is we find 3, and once again, we shade the area underneath the curve, the PDF curve that is, to the left of 3, and of course above the x-axis. Now technically, both the PDF and CDF have horizontal asymptotes here, so this never actually gets to 0. But if you shade this forever to the left, it's getting smaller and smaller area as we go out to the left. It actually turns out to have a finite area. The total area is 1 under the whole curve. The part we're shading turns out to be exactly 60% of that, or at least approximately 60% anyway, of that area, so that probability is 0.6. Now, it's pretty hard to tell by looking just at the graph that that's 60% or 0.6 is that 0.6 square units is what we have there, or 60% of the area. That's pretty tough to visualize or to compute. It's a lot easier to do it off of the CDF graph. So you take this 3, go up here, and see where it crosses the graph, and it looks like it's crossing very near, if not right on, 0.6 for the y. So you can think of it as this green vertical distance of 0.6 units, or this y value of 0.6, which is the probability to the left, which is this shaded region here. Okay, let's try another one. This time, illustrate and estimate the probability that x is greater than 5. Again, go ahead and do this on your own and come back. Press pause now. Okay, so we find 5 on the x-axis, and we want the probability to the right of that. Well, we can see it's to the right of that, maybe even better on the PDF than we can on the CDF, and that is this area to the right of 5. So the right and left thing maybe is a little bit easier to see on the PDF graph. Okay, but we know an area to the right then is a distance from the CDF graph up to y equals 1. So it's going to be 1 minus this y value. It looks like this y value is about 0.86. They're going up by 0.5s here, so that's just barely above the 0.85. So it looks like it's about 0.86. And so 1 minus that is 0.14. And that is this vertical distance here. This blue distance from here up to here is 0.86. The remaining distance up to 1 is 1 minus that of 0.14. So you can see it is this vertical distance, or as a difference of two y values on the CDF. On the PDF, it's an area under the curve. And again, that is 0.6 square units. I'm sorry, I didn't fix the slide from last time. Let's fix that. There we go. It's 0.14 square units, or about 14% of the total area under the PDF curve. All right, let's try between probabilities. Same CDF, same PDF, go together for the same distribution. Illustrate and estimate the probability that x is between -1 and 3 on this graph. Okay, your turn. Do it now. Press pause. Okay, let's try it. So here we're going to find the -1 is here, the 3 is here. And so on the PDF, it's this area, whoops, back up. It's this area between -1 and 3 above the x-axis, below the PDF curve. Okay, it's actually easier to read off of the CDF, however. What you do is you take the 3 and you go up and find its y value. And you take the -1, find its y value. Subtract those two y values. So this one to me looks like about 0.69 and this one about 0.23. Subtract those and you get 0.46, which can be seen as this distance vertically between these 2 points, not the slanted distance, but just the vertical change, which is the amount of this green distance here. So this distance here, this green distance, is the value of the probability we're looking for. And you can see that on the CDF, but it's numerically equivalent to this area here on the CDF. So the CDF probabilities or area, PDF, no, let me say it right. The PDF probabilities or area. CDF probabilities are vertical distances.